Hello everyone, welcome to Helm of Science. So in the previous classes we had started with a revision series wherein we have discussed some important questions that can come up for the upcoming joint entrance examinations, and the chapters that we have discussed are mainly chemical kinetics and electrochemistry, so that you can just revise the questions and keep yourselves updated as and when the exam happens. Now, at the moment, we are all at our homes and getting absolutely frustrated and bored. So, I believe this revision series will help you to keep your preparation ongoing without taking a backseat in it, and it will help you to revise your concepts thoroughly. So, without wasting any time, let us start with today's revision series topic, that is coordination chemistry. Now, coordination chemistry is a very important topic as far as your boards as well as competitive exams, whichever it might be, is concerned, because it actually forms a majority junction of the inorganic chemistry portion of your syllabus. So, this topic is of utmost importance, and I would just advise you to do this topic in as much detail as possible. So, let us begin. The first question is the coordination numbers of CO and Al. There are two compounds mentioned are. Now, before we start off with the answer, we need to know what do you mean by coordination number. Now, coordination number, as the name suggests, coordination number, as the name suggests, is the number of donor atoms attached to a central metal. Attached to a central metal. Now, one word I want you to notice very, very carefully is the donor atom portion. Now, what do you mean by that? Now, substances which actually donate the electron density to form a coordination compound with the metal are called ligands. I'm sure all of you know that. But now, which part of the ligand actually donates the metal is the donor atom. And the number of donor atoms will tell you the coordination number of a particular species. Alright, so starting with COCl En whole 2Cl, right? So here children, see, cobalt has one Cl, that's fine, and two En groups. Now what is En? En is basically ethylene diamine. If you want to know the structure, how does it look like? It is basically NH2, CH2, CH2, NH2, where the lone pair on the nitrogen atom acts as the donor center. So this is the entire ligand, but the donor atom is the nitrogen atom. Alright, so we have two ethylene diamines. So how do we do? Now since there are two donor centers, it is referred to as a bidentate ligand. Alright, what do you mean by bidentate? When we have two donor atoms. Okay. Right? So how many donor atoms do we have here? 1, 2, 3, 4 and chlorine being 5. So the coordination number in this case will be 5. Moving on to the next compound that is given to us. The next compound is K2Al C2O4 whole 3. Now C2O4 is oxalate ion. Oxalate ion, the ion formed when oxalic acid releases its two hydrogen ions. Alright, now what is the structure like? It is two COO minus groups bonded together, wherein the oxygen centers act as the donor centers. Now we have two oxalate groups, so let's just start drawing it. One is OOC, COO. This is one part. Another is this one, right? And another is That one right there. Correct? So how many donor centers are we having? 1, 2, 3, 4, 5 and 6. So the coordination number in this case is 6. So the answer matches to option number D, which is 5 and 6 is your coordination number. Now moving on to the next question. The species that can have a trans isomer. Now first of all, isomerism means when same molecular formula gives rise to two different structures. Alright. Now, cis and trans is possible when you have two similar kinds of ligands. I repeat, cis and trans is possible when you have two similar kind of ligands. Alright. Now, if we see this one, the one that is the first option, see how can you, or eliminate your options is, for the first option that is given in this question is PTENCl2, right? So if we start drawing the structure, what will be it? If I just suppose place the two Cl next to each other, so this is your cis structure and putting one En on the other side. Now if we want to make trans structure for this, we have to put the two Cl on opposite directions. In that case, we have to put the nitrogen on the opposite direction. But this is a bidentate ligand. So you cannot just break the bonds randomly because this is a ligand which is in totality. Right? You cannot break the bond just according to our own wish. Alright? So in this case, trans is not possible. Using the same justification, we can actually omit option number D as well, wherein the metal is just changed from platinum to zinc. Right? Now coming down to option number B, that is also not possible. Why? Because it has 3 bidentate ligands, right? So this is something like if I take the cis form, then one, this thing, ethylene diamine, second ethylene diamine like that, and third oxalate. Right? Like that. So this is the cis form because the ligands are next to each other. Now, if we want to make the trans part, suppose we want to make oxygen on the trans position, but that is not possible because oxalate is a ligand in totality. So to break that bond and to form a new species is not possible. So this will not give you a trans isomer at all. Alright? So the only option left is option number C. Folks, see carefully in option number 2, it is PTEN whole 2 and Cl2. Right? Now this is possible. If we draw the cis structure for this, this should be this one. Right? Now the corresponding trans structure will be what? When we put the two Cl on opposite sides. So just let us do that. In this case, we can just, without even shifting or breaking any bond, we can actually transfer the two ethylene on the opposite side, which is the trans position, right? So this is possible and this will give you a trans isomer. So your correct option will be option number C. Now moving on to the next question. Okay, the question says there's a reaction mentioned and you have to find out the correct statement, right? So first let us study the reaction. What is there? Now this kind of question is not there in your board syllabus. So I am very sure that you have not come across such kind of questions. So just follow the process that I am doing and be a little attentive. Alright. So the reaction states, this is one complex reacting with Br minus giving a certain product. Right. Okay. Now, if we consider the first statement to be correct, hypothetically, if we consider the first statement to be correct, now let us just check that whether it is actually justified or not. So what do? It says, if we take the cis isomer of this compound, then we will get two isomers as products. Now let's just verify that part. So I am taking the cis isomer. Cis means the atoms will be next to each other. So 2 bromine like that, 2 NH3 like that, and 2 NH3 here. Okay. So this is the cis isomer, and when we'll add the bromine minus, now this is a concept of new concept, a very new concept which you have not done, I'm very sure. That is trans effect. Now, you don't need to know what is exactly trans effect because it's a huge concept, but what you need to know is trans effect is when certain species which will enter into a complex will have a greater power to obtain the transposition than the given ligand in the complex. I'll repeat once again. Trans effect is the phenomena by which any entering ligand will have a greater power for this transposition as compared to the existing ligands. Alright. Now, according to trans effect series, bromine minus has a greater trans effect than NH3. So any NH3 which is in the trans position, it will try to remove one NH3 and get into its position. So these two NH3 are trans. Now bromine minus will enter one and throw out the NH3. So the product will be this. Now carefully notice one thing. There is a habit that we write NH3 just like that. Like, what I mean to say is some people write it this way. Now this is a wrong way of expressing. Why? Because this shows that you are making a bond with hydrogen. But hydrogen itself needs stability from other atoms to get or to complete its octet or duplet configuration. The duplet configuration, not the octet, the duplet configuration. So it does not have a tendency or it does not have any electrons to donate. So writing it this way, even though it looks like NH3 is wrong, you should show the atom which is forming the bond, as I have mentioned in this case. Alright, so now this is one isomer we have got. Another isomer that we can get is if supposedly bromine removes this ammonia, okay, from here, then what happens? NH3, bromine, H3N and H3, right? So when three bromine are on the same side, that is they occupy the same face of a triangle, that is called facial isomer, facial. And when two similar ligands are next to each other and one of the third similar ligand is at a position leaving one position after it, I repeat once again, when two bromine ligands are in the same position or next to each other and one of the ligands, that is the bromine ligand, is occupying a position leaving one position later, which is this one, that is called the meridional isomer. So from the cis isomer, we are getting two. One is facial, one is meridional. Right? Now let us check the trans isomer. So the first option is correct. We can see. So if the first option is correct, then logically your next option, that is, the fourth option, that is only one isomer is produced from the cis isomer, that is automatically ruled out. Now let us check option number. Okay, let us just begin with the trans isomer and we'll see how it goes. Alright. So trans isomer meaning all the ligands will be opposite to each other. Right. So let's just put the two bromine opposite to each other. NH3, H3N, like that. Alright. So the bromine and the ammonia are opposite to each other. Right. Alright. Now if we want to enter bromine minus, which has a greater trans effect than ammonia, so it will enter one of these ligands. Right. So it would be something like this. H3N and alright. Now if we want to remove this ammonia and enter the bromine, so we'll get another bromine on this side. Right. So it will be the same isomer. How? If the bromine is on this side, then two bromine together and one bromine leaving one place. That is meridional. And even this case, two bromine together and one bromine leaving one place aside. So both cases we will get only one isomer, that is the meridional isomer. And so it brings us to a conclusion that option number 1 and 3 is correct. That is option B is correct in this case. Alright. Now moving to the next question, that is question number 4, I believe. So the next question says that the pair of coordination complexes exhibiting the same kind of isomerism. Now, why have I chosen this question? Let me just tell you. See, it's a multiple choice question. Means more than one option is correct. Now, generally, whenever we are solving a question, it's a human tendency that whenever we see one option correct, we don't look at the other options. So, my motive to do this question was you notice that there might be more than one option correct. Alright? So, how do we do it? See, the first, if we start off with the option number C. Why do I say option number C? Because it's the easiest one. See, it has two complexes, COBr2Cl2, 2 minus, and just the metal has been changed, PtBr2Cl2, 2 minus, right? So if we start drawing, this will have a cis and trans isomer. How? Bromine on the same side, chlorine on the same side. So this is the cis form. And you'll have a trans form, bromine on the opposite side, chlorine on the opposite side, right? So similarly, since this metal is the same, we can draw the same structure for this. Bromine on the same side being the cis form and bromine on the opposite side being the trans form. Correct? Okay. So these two complexes show the same kind of isomerism, which is the cis-trans isomerism, or if you want to be a little more specific, it's the geometrical kind of isomerism. So that option is correct. So option C is correct. Now, moving on to option number D. See, in option number D, we have two complexes, PT NH3 whole 3, NO3Cl, right? And we have PT NH3 whole 3, ClBr. So this can show kind of ionization isomer. How? Just replace these two ligands in its position. So we'll get NH3 whole 3 Cl NO3 and we'll get PT NH3 whole 3 Br Cl. So when an ion from outside of the coordination sphere enters, thereby replacing one of the ions which is inside, that kind of isomerism is known as ionization isomerism. And both the complexes are showing that. So that is also a correct answer we can assume. So C and D are correct up to now. Right. But B, if you move to option number B, it's incorrect. Why? Because the first compound can show your cis-trans isomerism, no doubt about it. How? One would be COCl on the same side and NH3 on the same side. And what is the another way? The another way is CO on the Cl on the opposite side, right? This is another option. Correct? So this is cis-trans. But the option number 2 which is there, which is PTNH3 whole 2 H2OCl, that is a problematic species. Why is it so? Because, or rather, you can say that it can also show cis-trans, because putting two NH3 on the same side and H2OCl, right? And what would be the trans where the NH3 is on the opposite side, right? This is one. So we are getting cis-trans in this also. So this can also be a correct option. But if we quickly move to the option which we did in the first case, right? This can show, both of them can show cis-trans isomerism, but the hybridization in the two cases will not be the same. Why? Because platinum is lower down in the series. It's a 5D element. So that is why it will tend to show a square planar kind of structure, and this will show a tetrahedral kind of structure and not a square planar one which I have shown. This will not show a square planar structure. Hence, it will, if it is a tetrahedral structure, then it will not show cis-trans isomerism. This will not be shown. No cis-trans. So in this case, we have to rule out the option. Okay, that won't be a correct option. And leaving us to option number 1, let's just justify that as well. So option number 1 says CrNH3 whole 5 Cl and CrNH3 whole 4 Cl2. Now see, in the first case, you have 5 similar ligands and 1 dissimilar ligand. Now, you cannot have one dissimilar ligand giving rise to a geometrical isomer. You have to have at least 2, right? So that is why in that case we cannot, whereas in the second case we can have a cis-trans isomerism. So that is why option A won't be your answer. So your correct answers would be D and option number D. Alright. Now moving on to question number 5, which says the crystal field stabilization energy. Now this is one question which is very common in your boards as well as your joint. So I'm assuming that you know the splitting, but we'll just discuss the question as of now. So the first complex given is FeH2O whole 6 Cl2. Right? First things first, whenever you're told to do the calculation for CFSE or anything like that, you have to find out the charge of the central metal. Let us consider it to be X. Now water is a neutral ligand, so it will have a charge 0, and Cl has a charge of -1. So 2Cl means -2. So this entire complex to be neutral, the charge should be +2. Right? So X plus 0 will be +2, whereas we get that Fe is in +2 oxidation state. So Fe +2 means what? Basically D6 system, 3D6. Right? Now this is a weak field ligand. So there will be no pairing, there will be initially. So we'll consider, and it's an octahedral complex 6 ligands. So in the EG and T2G sets, we will first fill it singly and then we will pair it up because it's a weak field ligand. So our CFS, this would be the barycenter. Above part would be +0.6 and below would be -0.4. So our CFSE would be 2 into 0.6 plus 0.6 plus 4 into -0.4. This gives rise to 1.2 minus 1.6, which is equal to -0.4 delta. Right? Now, when you get this answer, automatically option C and D is eliminated because it does not match with our given answer. So we just have to see whether option 2 is correct. Now, what do you have? See very carefully. K2NiCl4. Right? Now, here there are 4 ligands. So this is a tetrahedral complex. First things first, please keep that in mind. Now, this will have a charge of, this is +1, so +2. This should be -2. Then nickel will be +2 charge. Now, nickel +2 is 3D8 system. And Cl being a halogen is a weak field ligand. So, since this is a tetrahedral complex, the T2G will be upwards and EG will be downwards. Now, filling it up singly first and then we'll pair it up 4, 7 and 8, right? So, this would be delta T, barycenter. This would be +0.4 and this will be -0.6, correct? So, our CFSE would be 4 into +0.4 plus 4 into -0.6, which will give us 1.6 minus 2.4, right? This would be -0.8 delta T and not delta O. This is a very common mistake that we make. Alright, so our option will be option number B. Moving on to the next question. The shapes of the complexes. Now, this is a very interesting question. When nickel 2 plus reacts with the given ligands are Cl minus, Cn minus, and I believe water. Yeah. So, what would be the shapes? Now, nickel or a D8 system is very important. Why? Because D8 systems have a very different kind of a logic. Any kind of D8 system, just listen to this very carefully. This will make your preparation very easy. Any kind of D8 system, when it has a weak field ligand, okay, it will give rise to a tetrahedral complex or outer or rather tetrahedral complex, giving the formula NiCl4 2 minus. When the DH system has, in this case this was Cl minus, it has a strong field ligand. DH system, strong field. In this case, cyanide, strong field, I mean the ones which are very high in the spectrochemical series. Alright, not the intermediate ones. This will give square planar complex, that is NiCN4 2 minus. And when you have a neutral ligand, supposing water or ammonia, it tends to give an octahedral complex with the formula NiH2O whole 6 2 plus. So your answers will be tetrahedral, square planar and octahedral, which is option number B. Right? So this thing keep in mind, that when there is DH system and the ligands are classified this way, then what would be the corresponding structures? Yeah. Moving on to the next question. The next question states that you have to say find out the metal ions given in the options below, which will give a magnetic moment, spin only magnetic moment of 3.9 Bohr magnetic. Right? Now before that, you need to know what is spin only magnetic moment. Spin only magnetic moment refers to number of unpaired electrons in a metal. Okay, spin only magnetic moment is equal to number of unpaired electrons in a metal. Right? Or metal ion also, you can refer to it as. Okay, so in that case, what happens? The complex given to us is MH2O whole 6 CH2, right? First things first, find out the charge of the M or the metal. That would be 0 minus 2. This should be whole plus 2. X. So X plus 0 equal to plus 2. Now see, all the options mentioned to you are in the plus 2 state, right? Now let us start. The first option A says CO2 plus and Fe2 plus. But before that, it has also been mentioned that the spin only magnetic moment is, that is root over of n into n plus 2 is 3.9 Bohr magnetic. Now just a small piece of advice and a trick which I want to tell you. Whenever you get the magnetic moment value like that, your number of unpaired electrons is equal to the value before the decimal place. In this case, 3. If your magnetic moment was mentioned to be 4.9 Bohr magneton, then your number of unpaired electrons would have been 4. Alright, now moving on. CO2 plus means a D7 system and this is a D6 system. Now water is a weak field ligand. So let's just start filling up the EG and T2G sets. This would be 1, 2, 3, 4, 5, 6, 7. So you have 3 unpaired electrons. Absolutely. 1, 2, 3, 4, 5, 6. In this case, you have 4 unpaired electrons, which does not match our given data. So this option won't be there. Moving on to Cr2 plus and Mn2 plus. Now let's check. Cr2 plus is a D4 system and this is a D5 system. Right? So this should be 1, 2, 3 and 4. Absolutely not the option we want. Right? Now moving on to next set of ions, that is vanadium 2 plus and cobalt 2 plus. Now cobalt 2 plus we have already seen that it matches the unpaired electron configuration. Vanadium 2 plus is a D3 system. So it has 3 unpaired electrons which also matches. So that is our correct answer. Now just verifying. So option C is our answer. Now just verifying option number D. Option number D has vanadium which matches our specific value. But Fe2 plus already has 4 unpaired electrons we have seen here. So that does not match our specific value. So that will not be the correct answer. Alright. Now moving on to the last question, which is also a new concept for all of you. That is charge transfer complex. That is not there in your board syllabus. But joint entrance examination has actually included that as a part of your syllabus. So we will not discuss very much in detail because that's not required unnecessarily. We will just discuss that much portion which is needed for us to solve a problem. Alright. So charge transfer is of two types. Alright. One is ligand to metal charge transfer and metal to ligand charge transfer. Now how will you identify which is what? So for ligand to metal, just note down these points. Ligand to metal means ligand will transfer its electrons to the metal. Right? So for that, the ligand should be electron rich. Only then it can transfer its electrons. And second should be the metal in the ligand should have a very high oxidation state. Should have oxidation state greater than equal to 3, which means it should be electron deficient. Okay. Whereas for MLCT, metal is transferring the electrons, so metal should be electron rich and the ligand should be electron deficient. The ligand should be L should be electron deficient. Okay, or pi acceptors. Correct? Now let us just come to the question which is given to us. See, KMnO4 is given, right, children? So KMnO4, if you try to find out the charge of the individual elements, potassium is +1, oxygen is -2. So -8 plus 1 is -7. So the whole compound to be neutral. Manganese should have a charge of +7. Now this is the metal, this is the ligand. What is the ligand? The permanganate ligand. Right? Permanganate ion is the ligand here. Now it has excess of electrons, yes, because the whole has a charge of -1, MnO4 -1. So this is the ligand is electron rich, criteria 1 satisfied. And the metal in the ligand has an oxidation state greater than +3, that is +7. So condition number 2 is also satisfied. So this is an example of LMCT. Now you might ask me, ma'am, what is an example of a MLCT? See, if we consider potassium ferrocyanide, ligands like cyanide are electron deficient or pi acceptor kind of ligands. Alright, the ligands which are higher up in the electrochemical series, like that of carbon monoxide, cyanide, these kind of ligands are pi acceptors. So whenever you see these kind of ligands, you will know that this should be a MLCT concept. Another thing, the metal here has what charge? Just see, it has a charge of +2. So this is not exceeding the +3 concept. So this can never be LMCT. Alright, this will be MLCT, that is metal to ligand charge transfer. Now there is one more option mentioned. Let me just explain it to you, which is DD transition, right? Now what is DD transition? When there is electronics transition between the d orbitals of a metal. Suppose I say that titanium 2+. So this is a D2 system, right? So when we are saying an octahedral complex, supposedly, so if we are saying that, then when the electron transfer is from T2G to EG, that is within the d orbitals itself, that is referred to as a DD transition. Alright, so in this case our option will be option number C, that is ligand to metal charge transfer. So these are the various questions which I thought, and all of the questions are of different kinds, which I thought would be examples for you to help in your preparation in a better fashion. So I hope you have understood all the questions. If there is any doubt in any of them, you can mention it in the comment section below. And if you want to know about any other questions which you have come across in any of the test papers, that also you can tell me. Alright? And just one tip, note down the 2 important concepts which are not there in your board syllabus, so that it will make your preparation take a better seat. Alright? So that's it. We'll meet in the next class with a new revision series. Till then, keep revising and stay safe. Thank you.